Starting off, our first talk I'm very excited about is coming from Carla Gomes, who is coming to us from Cornell University, who will be giving a talk titled Artificial Intelligence for Accelerating Materials Discovery.
Hello, I'm Carla Gomes. It's a great pleasure for me to give this webinar. I'd like to thank the organizers for this opportunity. I'm a computer scientist. My research area is AI. So today I'll give you my perspective on AI for accelerating materials discovery. In recent years, we've witnessed rapid progress in AI. AI systems are demonstrating superhuman capabilities on tasks that we consider intellectually challenging. For example, in 1997, IBM Deep Blue defeated Kasparov, the world chess champion. In 2011, Watson defeated the human Jeopardy champions. In 2016, Alphago defeated the Go world champion. This was a surprise for computer scientists since Go is substantially harder than chess. It has a much larger search space. So we didn't really expect this to happen this soon. In 2017, AlphaZero, a variation of the AlphaGo, taught itself how to play chess. This was quite an achievement. So all these achievements are quite remarkable. And in fact, now we see a rapid shift in AI research moving from the pure academic world into the real world. AI systems are radically transforming our daily lives. And of course, a good example is the iPhone with a variety of apps that make our lives simpler, at least in principle. For example, Google Maps open up a range of possibilities. And of course, we have the promise of self-driving cars. AI systems are radically transforming also business, medicine, and biology. For example, Wall Street often uses autonomous trading systems. Amazon has a highly automated supply chain system. Remote robotic surgery is now a reality, and genome sequencing has revolutionized and become indispensable for biological research. I believe the next frontier for AI is scientific discovery. Of course, the material science community is paying attention, and in fact, MRS just produced 2 special issues on AI and ML. The main trend in material science is focused on using machine learning techniques. In fact, this webinar is called The Machine Learning Revolution in Materials Research. This makes sense since the major recent AI achievements have been largely driven by ML, machine learning, and in particular by deep learning and big data. In fact, we can now say that machine perception is starting to work. In fact, after several years, AI systems are now starting to see and hear. We have very sophisticated computer vision, speech recognition, and natural language understanding systems. Our systems are also now becoming grounding in the real world. For example, Facebook now can reach superhuman face recognition, and NVIDIA can achieve superhuman traffic sign recognition. It's true that machine learning and deep learning have played a key role in the recent AI achievements, but we should also be aware that AI progress is also due to many other cumulative AI developments. For example, other areas of AI, such as problem solving, knowledge representation and reasoning. I already mentioned robotics, natural language processing, and vision. In fact, a particular area that is key for AI is, and in particular for scientific discovery, is symbolic AI. This area includes areas or sub-areas such as problem solving, search, logic, planning, constraint satisfaction, and optimization. I believe that the integration of machine learning and symbolic AI will be a game changer for AI systems. A good example of that is Alphago and AlphaZero. And even though we often think about Alphago as a machine learning system, de facto, Alphago integrates deep learning and reasoning techniques, symbolic AI in particular, Monte Carlo tree search, and reinforcement learning. So, the key challenge for scientific discovery is how to scale hybrid machine learning and symbolic AI approaches to real-world applications in scientific discovery. I will now talk very briefly about Crystal, a multi-agent AI system for automated mapping of materials crystal structure. Crystal integrates machine learning and symbolic AI techniques for crystal structure phase mapping. This paper was recently published in MRS Communications. I'll start by briefly describing high throughput materials discovery. Material science have devised a way of simultaneously synthesizing thousands of materials. Here we see a technique called co-sputtering, which is similar to atomic spray painting. So they can produce thousands of materials a day, and they can also use high throughput characterization to characterize thousands of materials a day. Here we see X-ray diffraction as an example. A key challenge is how to infer the crystal structure of materials based on the X-ray diffraction pattern collected. So as an example here, we have a ternary representation of a system, and the dots correspond to X-ray diffraction patterns, and they are all here stacked. So a key problem that is referred to the crystal structure phase map problem is how to infer the crystal structure of the materials from the X-ray diffraction patterns. This is a source separation problem, and it is challenging because often the X-ray diffraction patterns correspond to mixes of crystal structure, so it is challenged to unmix the X-ray diffraction patterns. And this is a task that requires expert knowledge, and it takes an expert can only analyze a few systems a year. So more formally, crystal structure phase mapping is given as input a collection of XRD diffraction patterns. We want to produce as output the M phase regions, including the K pure regions and M minus K mixed regions, as well as the XRD patterns that characterize the pure crystal phases. Well, this problem is more complex because we need to satisfy a variety of physical requirements that are thermodynamic rules. For example, the phase connectivity rule that states that the phases should be a connected component, the so-called Gibbs rule, and many other rules. So, but at a high level, this problem actually can be seen as what we say a pattern of factor decomposition or source separation problem. For the phase map identification, we are given XRD patterns, and based on the XRDs, we want to infer the crystal structure. But there are other problems that are computationally similar to this one. For example, we get recordings from a forest, and we want to identify the elephant calls or the bird calls and separate them from other noises. Or we have the problem of music source separation, where we want to extract or identify the instruments that are in a given song. Another problem that is also similar is what we call topic modeling, where we are given a collection of documents and we want to extract the key topics in the collection of documents. Mathematically speaking, this is a matrix factorization problem with combinatorial constraints. So we are given a collection of X-ray diffraction patterns or documents, let's say matrix A, and we want to decompose this matrix into two matrices, W and H, and W times H should approximate A. We define some loss function that we want to minimize, and we also want to make sure that we satisfy the constraints of a problem, namely that we should have non-negative results. The factors should be non-negative as well as the activations. And we also have to make sure that we satisfy the different thermodynamic rules. So this is a good example of a problem that involves standard ML approaches for minimizing this loss function, but it requires also symbolic AI for us to satisfy these combinatorial rules that correspond to prior knowledge. Well, this is also a good example why scientific discovery is challenging. For example, crystal structure phase mapping is an unsupervised learning problem. We don't have labeled data, and the main successes of machine learning, in particular deep learning, depend on large amounts of labeled data, which we don't have. In addition, we have to deal with noise, incomplete data, and uncertainty. And as I mentioned before, a key issue is the fact that standard machine learning techniques fail to capture the underlying physics of the phenomenon. In order to do this, we need to use a set of combinatorial constraints to capture the physics of the phenomenon. So Crystal integrates machine learning techniques with symbolic AI, in particular constraint and logical reasoning and optimization techniques. And our approach is also to integrate multiple knowledge sources and reasoning mechanisms. For example, combining XRD data with other forms of characterization of the data. Also using prior knowledge from materials databases, and also using human expertise if necessary. So Crystal solves the phase mapping as a constraint matrix factorization problem. Basically, Crystal integrates machine learning with the symbolic AI in order to produce a meaningful solutions. For example, here we see that this algorithm that is machine learning based, Agile FD, is a convolutive non-negative matrix factorization that performs the high level factorization of the matrix. And then Crystal has several specialized algorithms, constraint reasoning algorithms, to enforce feasible constraints. So basically, here is a visualization of Crystal's agents. So Crystal is a multi-agent approach for crystal structure phase mapping. And essentially, Crystal encapsulates a diverse collection of fast ML and symbolic AI algorithms with different types of knowledge and capabilities to perform phase mapping. In the picture, we see that, for example, Agile FD is an agent that is an ML agent doing non-negative convolutive matrix factorization. Then we have several symbolic AIs enforcing the different rules. We also use ML agents for phase dimensional analysis and clustering, and other ML and symbolic AI components for analyzing the solution. And also, Crystal also includes Phase Mapper, which is an interface and a visualizer for interaction with the user. We ran Crystal on the Palladio Rodeo Tantalus system with 198 X-ray diffraction patterns, and Crystal produced about 2,500 valid phase diagrams. From these valid phase diagrams, using a clustering approach, it identified 20 representative phase diagrams, and from those, the human experts select 5 for refinement, and from these 5, picked the final solution. Crystal enabled the discovery of a mixed intermetallic methanol oxidation electrocatalyst. A key component of Crystal is Phase Mapper that allows experts to interact with the solutions, analyze the solutions, and also provide feedback to Crystal's algorithms. This Phase Mapper actually received an Innovative AI Award, and it was the cover article of the AI Journal and the ACS Combinatorial Science. Let me now wrap up and talk about the future, in particular concerning autonomous systems for scientific discovery. Good examples of autonomous systems are Adam and Eve. These are robot scientists that perform autonomous experiments in biology. ARES is an autonomous research system led by Benji Marijuana at the AFRL, and ARES is the first closed-loop autonomous research robot for materials development. ARES learned how to grow nanotubes at controlled rates. We recently started a MURI project, SARA. SARA stands for Scientific Autonomous Reasoning Agent, and the overall goal is to integrate material theory, experiment, and computation. The big picture is that SARA will encapsulate the scientific method for materials discovery. SARA integrates symbolic AI, machine learning, and human-computer interaction, and SARA will be able to formulate hypotheses, plan and design experiments, and analyze the results of the experiments, integrating prior knowledge. SARA will have a large search space because we'll be looking at laser speck annealing experiments, considering typically ternary systems. So we have a three-dimension space for the compositions, but in addition, SARA will optimize with respect to peak temperature and dwell time. So this is a very ambitious project. We are at the beginning of this project, and it is a very exciting research area. And of course, we have a large team of computer science and material science. In fact, my colleagues in material science, we have experimentalists, Bruce Vandover and Mike Thompson at Cornell and John Gregoire at Caltech, and computational theorists, Chris Wolverton and Alex Zanger, and myself and Bart Selman at Cornell as computer scientists. So, in summary, scientific discovery is an exciting frontier for AI. I believe AI has the potential to dramatically accelerate materials discovery, but at the same time, this is a two-way street. There are many challenges posed by scientific discovery that will lead to advances in AI. That's why I'm so excited about this area. In particular, I believe the integration of machine learning and symbolic AI will be a game changer for AI systems. Thank you.
Okay, thank you, Dr. Gomes, for that fascinating talk. Dr. Gomes is on the line and ready to take questions, so please enter them in the questions tab. To start with, I can include a question that we have here, which is, Carla, could you elaborate on some of the opportunities and limitations that you see in the current state of the art in AI and ML for materials discovery?
Sure, and this is a very exciting opportunity for AI and for material science, and these webinars are really exciting. And indeed, I think, as I alluded in my talk, and Keith actually in his great introduction, there are so many opportunities and even low-hanging fruit for AI to speed up material science and discovering material science. And this is actually possible for several reasons. And I would say that one is, we now have a zoo of databases that are becoming available, some of them more on the computational side, such as, the Materials Project, the Open Quantum Materials Database, and the Automatic Flow for Materials Discovery. But there are many other databases that are becoming available. Another key aspect is, we have witnessed a big, I would say what I would call the democratization of ML with many open source packages that are becoming available, which is really facilitating and promoting the use of AI and ML. As I stressed, perhaps I would say concrete examples of success are described in these issues, and I would emphasize, for example, super hard materials, the identification of experimental verified new materials such as super hard materials, predicting new metallic classes, and, the cases that our speakers will be highlighting. So I think it is clearly a time for excitement and for us to really take advantage of these opportunities. To some extent, I also would caution the community, and my talk already raised some of these issues, that, what we are trying to do is really ambitious. We are trying now to use AI for accelerating scientific discovery, and that is a whole new facet. AI has progressed dramatically in recent years, but, the current state of the art of AI is more at what we call the perception level. In fact, machine learning is good at things that humans can do without thinking, like image recognition or, speech, etc., which obviously there are many opportunities to use that for accelerating material science. But there are challenges, and the challenge are related to the fact the main successful ML techniques rely on the availability of very large data sets of what we say labeled data, or examples where we have, in the X and the Y. Often the reality, we have a ton of data, but these data are not labeled. Also, often we are trying to develop methods, and we really don't understand exactly how the techniques work. So in science, interpretability is a key component that we haven't really been able to harness. And of course, again, also as Keith mentioned, these problems have often very large search space. They are very, what I would say NP complete or NP hard problems. So we need to really harness techniques to be able to scale up these problems and find solutions. But again, there are many opportunities. Active learning is, an area that is picking up. And so I think that despite the challenges, there are great opportunities, and, the challenge make it really exciting for us to do research in this area.
Great, thank you. So I'll read out some more questions. One thing, Carla, I'll say is that we have a lot of questions backing up, which is great, and I'd love to have the engagement. So maybe if you could try to aim for a succinct answer, we could try to get to a lot of different questions. So thank you. Okay, so this next question, is a very practical one. There are only so many elements on the periodic table. When would you anticipate the automated materials discovery tool would finish exploration of the full space of ternary compounds?
Oh, now that is no, of ternary compounds. Is that? Can you repeat the question? But
it was.
What?
Sure, it was a question about when the tool could finish the exploration of the full space of ternary compounds.
Well, I think, that is when you talk about ternary compounds, I mean, there are still many other variables that you can manipulate. For example, I mentioned how, Sarah, we are going to look at ternary compounds, but then we are doing laser spike annealing. So we have two other parameters, the temperature and the dwell time. So we are now already talking about five parameters. So this is a large search space, and I don't think this will be anytime soon to fully explore the set of ternary compounds. Just another thing that I want to highlight. We talk about Alphago. Alphago is a very simple baby example, and just look at the amount of computation that Google has thrown at it. I mean, it's just remarkable and very simple rules. So that's exactly my point. Don't underestimate how formidable these search spaces are.
That's an excellent point to not neglect processing. Okay, so the next question is combining a couple of questions about the availability of data. So it seems like we need large open data sets for ML to work well. So how do we combat the problem of closed data? And then furthermore, a lot of federally or internationally funded systems like the European neutron sources, for example, have data embargo policies. Are there policies that we should be aware of or practices? How can we, moving forward, have better practices for sharing data and combating the closed data problem?
Yeah, that is an excellent question. And I have to say, as I mentioned in my talk, I'm a computer science, and I have been part of several communities. And, for example, verification, algorithms for software verification. And the key reason why we have made incredible progress over the years is that whatever we do is completely open source in terms of data, in terms of software that we can share, that we can edit. So I think that is, I would say, a sine qua non condition for progress. And I know that my friends and colleagues at NIST are really, pushing that, and I applaud, and I think that's what we should do. In fact, I mean, just as an example, for those who have done a bit of machine learning, there's a data set that is used for training examples that is super used, that is with handwritten characters. And there are thousands of papers using this data set that actually is called MNIST because it was released by NIST. So I do think that we do need to push for open databases and even software. Of course, I imagine all my code, all my research has been open source. I always make all everything available, and I think we should absolutely do that. And I'm not being as brief as Keith would like me to.
Okay, and just to follow up on a question that was raised in the chat, does that mean that Crystal is available to interested parties?
So the code is actually, Crystal as a single system is not available because that would be a little complex. But we actually have available the heart of Crystal, which is the algorithms, and we are actually have we are in the process, actually, we are working with the Toyota on making phase mapper available, which is really, the interface for Crystal. So yes, absolutely. And I have, my webpage, we have this, you discover it, you will have access to the code.
Fantastic. So just maybe if we had a lot of questions about different kinds of materials this could be useful for, why 2D materials are our current focus, if this is useful for other classes of materials, and can you just maybe very briefly comment on, if there are certain classes of materials for which you think this approach is particularly useful or maybe difficult to apply?
Well, I am a computer science, so that question, I think it is more appropriate for my colleagues.